Alright, time for another DraftScience video presentation. Probably eventually get to kinetic energy, but we'll start with the problem of ether theorists versus particles. Our versus just plain, functional energy. Sorry, might be some noises. They're putting a new roof on next door. Blah, 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 blah. Anyway, it's hard to conceptualize experiments that might conclusively settle the ether versus particle question. When I thought about it, I said I haven't spent much time on it. As I've sort of stated before, I don't see anything intuitive about ether at all. But I must concede that apparently a lot of other people do. I mean, people gravitate to the Ken Wheeler types, and they seem to think the universe has to be made out of stuff and stuff. That there can't be nothing, so to speak. And I don't really get that at all. So it's never really occurred to me to even think about it. It's so like trivially unuseful, an ether. So I sort of had I've said, I sort of like the way Einstein put it as superfluous. It, doesn't answer any questions. It doesn't provide for any functionality. It's and the irony, the funny part is that Einstein's thought about it was exactly the opposite of what I understand, in the sense of the problem of ether comes up with the problem of movement. And Einstein was of the opinion that's sort of opposite mine, in the sense that the ether has to be, it's the argument about a dead ether. A dead ether is useless to the universe. In the sense that if it's just carrying information, because it wouldn't explain gravity. So you could argue that one of the biggest problems for an ether theory is how do you account for gravity with an ether theory? Because then you have to have the ether go somewhere. If the ether is being pulled, then you have moving ether, which is essentially what I'm arguing for, which is there's already forces in the universe that are all moving. It's really hard to duplicate the idea of somehow there's waves of gravity, in the sense that we don't see that gravity has any frequency, that gravity's pulsing in some way. So in a sense, you have to really perceive the universe as being made out of energy that's being pulled into. And being pulled into, leaves you with all kinds of problems, when if you understand it as being actual energy that's pushing into things, and that some of that energy is absorbed, that is, the movement of that ether is absorbed, that works. But absorbing would again be the trick, is what do you do with the leftover ether? Once you've taken its energy, what does it do? What does it become? I suppose you could use some argument that planets get bigger or something. The ether expands everything in the universe or something, and so that would work for some people, because then they could have their growing Earth theory or some other kind of crap. But anyway, so I argue against ether just because it doesn't account for something. Sorry. The forces that you have to create in the universe, like charge and gravity and all that stuff, which in my opinion, does travel in straight lines and does all that kind of stuff that ether really doesn't going to make any sense for. You just can't line up the dominoes. You just can't arrange the dominoes in any kind of geometry that allows for straight lines from any position. So, a straight line between any 2 points. Sorry, it's distracting. Alright, so anyway, back to the question. Back to the comment. Your little... Okay, they're walking on the roof and their shadows are cast on the wall. Okay, got it. Okay, your little electronic breadboard gift reminded me of one my parents bought me when I was 9 or 10. So yeah, this is just kind of a quaint thing that, be interesting just to, what was the trigger for people who, generally speaking, are mechanically inclined. That is, they have some connection to understanding mechanics. Now, I would have been there no matter what, just because even before I had that, I had already taken apart everything in sight. I mean, I was just notorious for. It's like I wanted to know how the clock could tell time, that kind of stuff. I was just always really interested in how things worked. I mean, every now and then I lived in Louisiana, my parents would have crayfish or something, and there'd be all these little crayfish, in the sink, and I was just fascinated by what the fuck. How do these things know how to do their little, how does this little animal know how to do all the things it knows how to do? And cockroaches. I mean, there was things to keep you interested in assessing the world you exist in, and figuring out how all these things, there's snakes, there's all, all this, like I said, all that I wanted to understand. And I didn't take the animals apart, but I did, when somebody killed my pet lizard, doing us a favor, I did bury him and then dig him up just to see, what the fuck, what happens. So anyway, I mean, I was already on a path of deconstructing what it was to be alive, and so it sort of makes sense. By the time I was 10 or 11, I was already dissecting myself in terms of recognizing the corruptions of my own psychology, and how I was definitely doing that what's in it for me thing way too much. And this is a real dilemma, to live in a world where, you personally have to carry the burden of having a welfare stake, and yet you're supposed to be decent enough to understand that all the other welfare stakes are just as important. And that's a terrible conflict to have to exist with, and so it basically made me insane. And so that's the road to ruin, in a sense, because you just realize this is a meat grinder and a feudal system, and you just can't get too enthusiastic because it can all be taken away tomorrow. And then in my early 50s I had a stroke, or late 40s, and that was another lesson in why invest in anything, because that fast your investment burns up. Anyway, you can't hold on to anything. You can't keep your parents, you can't keep your cat, you can't keep anything. Anyway, so it all fucking sucks. But anyway, that's a separate subject, I'll concede. But, it's incidental to this conversation in some way, so I'll make an excuse for me getting away with it. But please keep your comments on the subject of physics. Anyway, I'm probably quite a bit older than you. I don't know if you can be that much older without really being in trouble. So the kit I received had more antique electronics boards than the one you're showing. I think it had the older germanium type transistor. Well, that's all mine had, ATB thingy. I mean, it was pretty simple. Or a couple of them, a speaker, a few indicator diodes, resistors, capacitors to make a simple radios or oscillators. Right. Well, I think that was basically mine. Mine didn't have the integrated circuits yet. That's all I remember. So there has to be a version that didn't quite get there yet, as far as I remember. I had a really big meter for measuring things, and because the LEDs weren't a thing back then, some flashlight lamps for use in projects. Yeah, that was something that seemed a little lame, was the little flashlight bulb. But yeah, but then when I went to work and found out, well, it was $10 for 5 LEDs. They were pretty expensive. The interesting thing was, by like 1980, you could actually buy a laser diode. But they were $25 each, okay, and they only lasted 7 hours. So they, basically what's in the 50-cent laser pointer was $25 and lasted 7 hours. So anyway, like you, I cannibalized the board for parts. I got me interested in radio generally, so I ended up with a license. That's the reason for the DIT dash stuff. Yeah, I guess I was doing the dot dash, you know. And so my brain just doesn't do dot dit. It does dot dash, you know. I guess too much Edison in my background. In my screen name, LOL. So I did know that at one time, and I forgot it. So sorry. Don't mean to rag on the name. I guess it was dot dash, then I would probably have gotten it. But then I'd still be irritated because it's like, why are you sending your name in code? I don't want to have to go look that up. It might just be SOS, you know. I'm like, oh, okay. It's just saying help. So anyway. All right, so enough of that. And so we'll go on to kinetic energy. Just thought I'd read it because it is a familiar story. And for all the people who probably do go through life and pick things apart, it's something that facilitated that internal, because it's really not a group project thing. You know, it's like you discovering. It's like you taking your magnifying glass and going out in the world and discovering. And so that at least it's a shared experience that I can have with some other humans, because generally speaking, I don't have too many shared experiences with most humans, apparently, because I don't understand how they work at all. I mean, it just seems so fucking stupid. And, you know, you're like, shit, did we grow up on the same planet? You know, I mean, I don't get along with other cultures, but getting along with our own culture, I don't even get, you know. Frankly. Pretty much. Anyway. Oh, that shadow is just... Anyway. Alright, so kinetic energy. Let's talk about it a little bit. Okay, in physics, kinetic energy of an object is the energy that it possesses due to its motion. So everybody could agree to that nice little statement. But that we could also just say that's exactly what momentum is. Momentum is the energy you have based on your motion. And you have two choices. You can give that energy away to friction, that is interactions with little tiny things that'll take the energy away, and with the form we'll call heat or vibrations or sound. Or you can have a more substantial interaction with some other substantial object and transfer your energy. Now the transfer might be, depending on the circumstance, where you hit something that actually rebounds you and changes your direction. So you keep your energy, you just change your direction. And these are the possibilities that are provided. Okay, I'm just going to mock all of this as being insanely simplistic, and it just jumps way over a ton of facts to make these statements. It is defined as the work needed to accelerate a body a given mass from rest to its stated velocity. So, this idea of what qualifies as work is where this sort of falls apart, because lots of circumstances don't look like work, like when you plow into a rubber stopper, or and it pushes you back, and the little bits, the friction bits, most people don't think of that as work. I did work on the surface, and therefore, it doesn't feel or look like it. Okay. And acceleration really doesn't have anything to do with it, in the sense that, yes, you're decelerating, but you're decelerating because you're losing your energy. So, I mean, if acceleration and deceleration were purely understood as not being some higher process than merely gaining or losing your energy, and that there's rules that govern how that can take place. But like I've just suggested, the rules are different for friction than they are for, banging into another person. All right. Stated velocity. Having gained this energy during its acceleration, So who has the energy is under debate, because of the relativity argument you could make, the physical relativity, not Einstein style relativity, but just the idea that we observing could be moving with one of the bodies and not realize that the real energy is in A, not, B is standing still and A is moving, or whether, A is standing still and B is moving. And so the trick is we're talking about a body having the energy when maybe it really doesn't. The other opposite one does. The planet Earth could be flying into an asteroid, so to speak. It could have velocity in a direction and be adding to the velocity of the asteroid. So we could say the asteroid's going 21,000 miles an hour, but no, the asteroid's actually only going 10,000 in absolute space, and we're adding the other 10. So that's sort of an important distinction, that something has to carry the actual energy. So it's kind of silly to say it's all relativistic, because something's carrying it. Something actually is in, if you just took a place in space and called it nothing, called it not moving, and the rest of the universe was moving relative to that frozen space, it does have an absolute energy. Something has it and something doesn't, and that's a truth. And it's just not a truth we can see yet, because we can't quite see those patterns inside the object. We can't see the shape of the atoms. I would kind of argue that the shape of the atoms probably is an indication of motion. So if we could actually see the shape of atoms, how distorted their circle is, let's just say, or their shape, then we could see which way they were moving and how much they were moving by how distorted their shape is. All right. State velocity. Having gained this energy during its acceleration, the body maintains its kinetic energy unless its speed changes, unless it encounters something. So unless it encounters something that it can exchange its speed with. So its speed can only change if it encounters something it can exchange with. That's the basic theory. It has to exchange it with something, some kind of interaction. And if there's no interaction, then there's no capacity to exchange the velocity. So something has to interact with it that has an opposite speed for it to give, momentum to it. It has to interact with something it can give its speed to. It's probably a simpler way to say it. And the tendency is for heavy things to give their speed to lighter things, not the inverse. But that's a whole nother subject. The same amount of work is done by the body when decelerating from its current speed to a state of rest. So again, they're using this term work, which just has a technical definition, not a real definition. See, the technical definition would be, I use work to raise the battery to a location, but I'm not doing any work to hold it here. And obviously you could figure out, no, I'm doing a lot of work holding it here. Holding it here is just as much a pain in the ass as it was lifting it. So, that's where it gets tricky. Just like if I compress the spring, there's no denying that it's pushing on the whatever's doing the compressing, but it pushes forever. So it's a loop. So it's creating a current of a kind. Right? If I compress this spring with say I have a solid object, so it's pushing into the solid object, and then it has a little bit of metal that comes out and holds the spring compressed, and the spring is constantly pushing in both directions. The trick is that push is like electricity, is somehow recycling, because it's not leaving the thing that's compressed. The pressure is being maintained perpetually until the release point, and that's when it becomes electricity. So it's sort of like a battery itself, in that the energy goes in and just sits there in a chemical form where it's held inside the battery. It's trapped, and it's not until you release it that it becomes this thing that can go forever, perpetual in a direction, or that can do work. It doesn't seem to be doing work when it's in the battery form. But the fact is that, yeah, it still is working. It's just working in a closed system. So it's doing work in the battery, but it's not doing work in the world. So it would be that kind of comparison, that the energy is always working. It's just, when do we see the work? When it's in a trap, we can't see it. Okay, in classical mechanics, so this is what's really annoying, is when they say in classical mechanics, when there was nothing classical about this energy theorem. The classical theorem was Descartes and Newton. That's the classical mechanics. Momentum is the classical mechanics, and let's understand there was no reasoned flaw in momentum as a mechanical theory. It worked really well. Again, everything Newton described, he described very thoroughly and carefully and well. And it all functioned the way he predicted. So momentum was working really good. And it really didn't need to be replaced. There wasn't some obvious or glaring flaw where, something was doing something that just was too weird, So it really didn't need to be fixed. It wasn't broken. It didn't need to be fixed. And the only thing they used to fix it, quote unquote, was aberrant experiments. So they took not the normal experiments, not the 90% of everyday life kind of experiments. They took the aberrant ones, the ones that looked funny, to justify the existence of this new physics. So anyway, I'm just saying, it's just really annoying when people use this rhetoric, classical mechanics. I mean, all there are statements, and they have either they have truth value, or they have shit value. And there's just no, this idea of comparing it to classical, or calling it classical, when no, it's austere, you could say. Austere mechanics, rudimentary mechanics, not wooey mechanics. I mean, that's how I would describe it. You have solid rational mechanics, and then you have wooey mechanics, and that's, to me, the distinction. All right. Anyway, so it's just wrong, okay, to say that anti-Newton physics is classical mechanics. I would say, if you're going to use the word classical, it should be that you're really talking about Newtonian error mechanics. All right, classical mechanics, the kinetic energy of non-rotating object of mass m traveling at speed v is 1/2 mv squared. So this is obviously not the classical formula. The classical formula would be momentum, and in the classical form, it didn't have the 1/2 in front of it. So they're implying that the old formula, the classical formula, was 1/2 mv squared, when no, it wasn't. The one that was a push against Newton was just mv squared. So we already know it was way, way, way off. Okay, so like I said, this is what propaganda looks like, right? I mean, these are just inaccurate, distorted phraseology to imply a truth rather than state the actual truth. And this implies that 1/2 mv squared was some sort of Descartes or Newtonian physics, when it really wasn't. Anyway, in relativistic mechanics, and they don't mean relativistic in the Galilean sense or even in the Leibniz sense. They mean relativistic in the sense of Einstein's wooey bent space-time thing. Anyway, this is a good approximation only when v is much less than the speed of light. So, yeah. And why should it be just an approximation? Why shouldn't it be pretty close to the truth or accurate? I mean, frankly, why are you saying it's only an approximation? It should be pretty explicit. There should only be the one source of energy. Energy should only be one thing. You either are working or you're not working. I mean, those shouldn't be ambiguous definitions. So anyway, this is really mushy talk. So, all All right, the standard unit of kinetic energy is the joule, while the English unit of kinetic energy is the foot-pound. So you don't need the foot in front of the word pound. You can understand a joule as just being a weight, a number of pounds of weight. So a newton is a quarter stick of butter. A joule is the quarter stick of butter after you let it fall 1 meter. So it, bang, it hits. And it hits with a certain amount of weight. So if you have one of those little spring scales, you could just watch the scale go to a maximum point. You'd say that is its weight. And it's going to be about a pound. Something like that. So it's not a foot-pound. It's a pound, essentially. Almost a pound, I'd say. Pretty close to it. I don't know. Nobody's dropped a stick of butter on a scale, so we just don't know for sure. But anyway, that'll be the simple answer. So it can all be understood as pressure. It's amount of your mass gains weight, right? So your weight gains weight as you move it. That's the simple argument. And that's how energy can be understood. As that when a mass is just sitting somewhere, if it weighs a certain amount in gravity. If there's no gravity, it doesn't weigh anything and it doesn't do anything. But if I move it, it's just like gravity. I'm now giving it motion, and if you give it motion, you're increasing the weight of the mass. It's a simple way to understand. Whether your gravity moves you at 22 miles an hour down into a scale, or whether I take the scale and put it this way and then have you move 22 miles an hour into the scale, it's exactly the same thing. You're just weighing the momentum. You're just weighing the mass. And if the mass is moving, it weighs more. It's that simple. It's a simple way of understanding. All right, anyway. So history and epistemology. The adjective kinetic has its roots in the Greek word kinesis, meaning motion. So at least that's reasonable. The dichotomy between kinetic energy and potential energy. So that's a whole different subject, right? Because potential, you can either be potential in the term of where the energy is trapped. So we know we're trapped in gravity, and that's kind of obviously a kind of energy that's constant. And then you can have the energy inside the battery, where it's just energy that's caught in there, it's spinning around, or moving back and forth, and it can't get out. All right, so until you let it loose, it's just trapped in there. And so that, to me, that's a good way of understanding it. But we're really not talking about the distinction between kinetic and potential. See, those you get that ingrained as a kid, that somehow there's two forms, active energy and inactive energy. And those would be better words than kinetic and potential. Because the potential, in gravity, you don't really have any potential. I mean, you go up in gravity and then you stop. Yeah, you have what's called potential energy, but it's not your energy. It's the energy of gravity, and you have to collect it. I mean, you don't have it. Gravity has it. Okay, the rain is going to push you down. You're not going to be pushed by nothing yourself. You're not going to fall naturally. You're going to be pushed. And being pushed and doing it yourself are two different things. Okay, being accelerated and having a velocity, not the same exact thing. Anyway, can be traced back to Aristotle's concept of actuality versus potentiality. So those are reasonable concepts, but they have nothing to do with kinetic energy. So it just really shouldn't even be in this description of kinetic energy, in the sense that that's almost a silly, superfluous, abstract element. There really is just recognizing that energy is, the obvious fact that if there was a 10 million asteroids heading for Earth, that you could call that potential energy, because you could stand in front of it and the avalanche could push you. But why would you even talk about that in those terms? That's not your potential energy. It's obviously the energy of the avalanche. That's what's going to move you. So why are you saying it's my potential? You know what I mean? You gain potential energy by standing in front of an avalanche. Duh. But it's not really your energy, it's the avalanche's energy. All right, the principle in classical mechanics that E is proportional to, instead they're not using equals, mv squares. Okay, so let's understand the original formula was that far off. Completely 100% wrong, because the half wasn't there. So it was a huge exaggeration. So instead of the 8-pound bowling ball giving you twice as much energy, it gave you 400. So if the 16-pound bowling ball has 100 joules, the 8-pound bowling ball has 400 joules, because of how far off this formula was back then. It was first developed by Gottfried Leibniz and John Brunelleschi. I don't know how much he had to do with the development of it, so not too sure about that. It really is Leibniz who made this bold assertion, who described kinetic energy as the living force, right? Not a very good scientific description. As descriptions go, sounds pretty wooey, religious, and nonsensical. So anyway, and then William Gravesend, whatever. So this was the guy who did the clay experiment. So it says it right here, okay, of the Netherlands, provided experimental evidence of this relationship. So they're saying overtly here that this is experimental evidence. And the physicists know it's really bad experimental evidence. The fact is, springs won't draw the same conclusion. They'll get completely different results. Other ways of measuring the weight, the joules, the pounds, will not see what the clay saw. So the actual, this isn't experimental evidence. When you're misinterpreting an experiment, you shouldn't call that provided experimental evidence, because it's really bad evidence. Okay. So by dropping weights of different heights into a block of clay. So this is the one aberrant experiment they used to defend the silly theory. So they found a mechanism that has a huge bias for velocity. That is, the faster the energy is moving, the faster the object that has energy is moving, the less the clay can stick to it, and therefore the less the clay can pull energy out of it. So it's like the clay is a thermal sink, and the fact is if you go through it with enough velocity, it literally can't thermally sink. It can't stick to the thing moving. It needs time. It doesn't have enough time to adhere to the object to pull its energy out. So the fact is that the slow-moving object gets slowed down much quicker because it can stick to the slower object, and any speed you add to the object, the less it can adhere to it, therefore the more freely it moves through the clay. And so it has the experiment has a grotesque and gigantic flaw in it, where it can clearly be understood by any fair scientist who analyzes the experimental device, the device you're using to see with, the device you're using to measure with. Any good, reasoned physicist knows clay wouldn't be what they were using. If they were using it to decide how much morphine, to give their dying mother, they would say, no, don't use clay. Okay, that's the wrong thing to use to decide. And because they know it has a bias. They know it's not going to give them a good measurement. So they wouldn't use it if it was a thermometer for their baby. They wouldn't use this evidence, this experimental device, if anything that would affect them would be at stake. How much virus, how much vaccine they get, how much medicine they get, how much food they get, how much anything they get. They wouldn't want clay to be deciding, because they can know that clay isn't a good thermometer. It isn't a good ruler. It's not reliable. And they would, I'm just saying, I don't think there's anybody who has any real knowledge of the physics would in any way attempt to defend clay as a good measuring instrument. So here we have just one aberrant experiment that has a clearly understandable bias, and the aberrant results are completely understandable, and somehow this side won. The side that has all the scientific, most 99% of the experiments are consistent with momentum being the right answer. These tiny little class of experiments can be, make a subtle visual argument. Okay, seems like there's got to be more energy, and somehow the seems like side won. And I'm just saying that's just a historical fact, and you'd have to say, wow, that's a pretty big mistake. How did that happen? Why did that happen? And it just has to do with politics. It has to do with just how governments change and how blah 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 blah, and what scientists had more money, or what country had more money, who got to talk louder than who. And it's there's not going to be a single good reason, because reasonable scientific scrutiny, Clay wouldn't have survived as it wouldn't have survived getting introduced to the trial. It would have gotten disqualified as an expert. The Clay wants to be an expert in the trial and testify, blah 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 blah, and clearly through the process of voir dire, they would have figured out that Clay is an asshole, and that no, you can't trust Clay's opinion, so Clay can't talk in the trial. So any Clay experimental evidence is going to be thrown out of the trial because it's clearly biased. It's clearly not a good measurement. And that's really the truth, and that's all I'm arguing here, is that this is a glaring error made in physics' history. The error is so obvious in the sense that, again, the formula was first introduced and it was already insanely way off. And so what are you reclamating? Why are you trying to reclamate something that has nothing good on its side? It exists out of pettiness. Newton's worst enemy invented this. So let's understand, Leibniz was the guy accused of stealing Newton's calculus. Not an unserious crime. He had huge huge motive to discredit Newton, rather, quite obviously. So there's just absolutely nothing good in this story about why this would be good physics. Everything about it has the smell of this is going to just be bad physics. You're going to do really bad science when you have a bunch of emotional pettiness at the core. Just like you see the Stephen Bro video that's just about trying to say Gary's an asshole and an idiot and a moron and a loser and a liar and all this other crap, when what he actually did in the video was basically prove Gary is right. Okay? The best experiment, the one most likely to get reliable results, is the one he mocked and ridiculed for no reason whatsoever, without any reasoning provided as to why springs are a bad source of energy, an unreliable source of energy. So this is what you get, though. This is, and here our people are just repeating the past right now. They're using the same propaganda tactics, the same lies and deception to fool people. That's all. Yeah, and it's just sad, pitiful. Anyway, by dropping weights of different heights into a block of clay. So, same guy again, Williams, Graves, and E. determined that their penetration depth was proportional to the square of their impact speed. So what he found is that, like with gravity, gravity is like clay. You throw a light thing into gravity, it doesn't collect as much energy, it doesn't slow down, and it goes 4 times higher. Half the mass, 4 times the height. Same thing in clay, okay? So twice the velocity, 4 times the depth in the clay, because the clay has a bias for velocity. It'll cut fast things a lot of slack. And it's probably a very good way to word it. All right, determine that their penetration was proportional to the square of their impact speed. And then we get into Emily de Châtelet, or however, recognized the implications of the experiment and published an explanation. Now, I can't find her actual paper. So if somebody can actually find the paper, translate into English and all that kind of crap, I would be interesting to read her explanation. But what I understand is she was clearly a believer in, metaphysics, free will. So a lot of the explanation is going to have to do with some sort of, we have, energy from God kind of bullshit. Anyway, the terms kinetic energy and work and their present scientific meanings date back to the mid-19th century. So this is just now jargon. So what words we use to describe energy. So energy was basically described as the quality or quantity of motion. Certainly Newton understood it as a quantity. Okay, whether what the quantity was in the object or not in the object wasn't relevant to Newton. He just said it either is or isn't moving, and this is the consequence of movement. So again, Newton was very austere in that he seldom attempted to explain a phenomenon beyond describing how it works, not why it works. Early understandings of these ideas can be attributed to Gustav Coriolis, the Coriolis effect, right? Famous for it, who in 1829. So now we know we're way past, So this Leibniz, they go from Leibniz, which is 1668, and all of a sudden now we're in 1829. I mean, shoosh. Published a paper titled blah, 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 blah. And then Lord Kelvin is given the credit for coining the term kinetic energy in 1849-51. Well, they also said in another paper that it was Young, of the famous Young experiment. So, so we'll do a little bit more. Energy occurs in many forms, including chemical, thermal. So all these forms of energy, you can say it comes in, but some of them we can see and some of them we can't. So you could argue that the chemical energy we can't see until it's freed. So it's invisible, it's a trap. The it's like the nuclear energy. We can't see it until, and to some extent, I suppose you could say that the radioactive elements are giving you some indication of their energy because they're leaking. They're like a leaky battery. So a leaky battery is sort of giving you an indication that there's energy to be had. All right, thermal. So thermal we can see, we can measure. Electromagnetic radiation. So that really does have to. You can see it often. You have to move the motor. You have to move things. You have to move the magnets to pull any of that energy out, to gain any of it. And if you want to create magnetism, you can see the electrical bill, and you can say, oh, I had to put energy in to get that energy out. I mean, magnetism is far from... the electromagnetic radiation clearly has a trail. You can follow the trail of the energy. Gravitational, well, that's the dead one, right? They call it gravitational energy, but why are they doing that when they're arguing there's no force that's creating it? So that's where it just gets, whoa, that's a big empty. We don't get to follow along. So we know energy is, you can never kill it. Well, gravity has every, appearance of being the death of energy. But regular physics won't say that. But you certainly can't see where it goes. You see that things move into the piece of mass, but you don't see how the energy ever gets back out again. There's no illustration of any, it keeps going. Yeah, nothing. Electric energy, elastic energy, nuclear energy. So elastic is just electromagnetic in a different form. Or you could even argue chemical in the sense of making molecules bigger and smaller and creating pressure that way. And then rest energy is that's just the baby talk of physics. There wouldn't be any rest energy if you could really rest. The point is that nothing can rest in the universe because there's a bunch of stuff constantly hitting it. Kinetic energy is the movement energy of an object. So that's okay. That's a good one. Movement energy. So why don't we call it movement energy instead of kinetic energy? That would solve a lot of problems, wouldn't it? Be a little bit more direct. Your movement energy. Yeah, that's, so much better. I mean, it really would be better. I mean, it's not entirely a joke. The physics would be better if the terminology was more direct, and that is just so much more direct. Kinetic energy can be transferred between objects. It is always transferred. That's the only way the only way you can gain it or lose it is to transfer with something that has it or doesn't. So it's always about transferring it between objects and transformed into other kinds of energy. So the transformation isn't really anything more than momentum. And all you're doing is you're making something big is moving, and then you make something small move. But it's all moving. It's all got a mass and a velocity. So all you're doing is taking a mass and velocity that are all doing one thing, and you're just leaking it to other things that'll do exactly the same mass velocity thing. And the rule sort of is that you can only do it in the heavy to light thing kind of way, not the light thing to heavy thing kind of way. One path is much more difficult than the other path. And well, I don't want to say that too overtly. You can't give velocity to something if you don't have the velocity to give it. You can't give it more velocity than you have, if velocity is what you're exchanging. And so I guess the underlying theme here would be, yes, you can exchange mass with an object, but that's different than exchanging your velocity. And that most of the exchanges will take place by you giving velocity to something. You don't give something your mass, you give something your velocity. But your momentum is, in fact, made of your mass and your velocity. But your velocity is usually what you're exchanging. Okay. Where did I leave off? Kinetic transferred. Yes. Okay, we did that. All right. Kinetic energy may be best understood by examples that demonstrate how it is transformed to and from other forms of energy. For example, a cyclist uses chemical energy provided by food to accelerate a bicycle to a chosen speed. Right. Well, he pushes on pedals, and the pedals are in a circle, and makes a wheel spin. The wheel has friction. So there's lots and lots of inefficiencies and lots to account for in the actual conversion of energy. And you could almost argue that it is our temperature that gives us the energy in a sense. I mean, obviously cold-blooded animals have mobility, but they only have mobility when they've been warmed up. Anyway, a chosen speed. On a level surface, this speed can be maintained without further work except to overcome air resistance and friction. Yes, in space you would keep moving. In an atmosphere you won't. On a surface you won't. The friction will transfer. You'll transfer your velocity, the velocity of the machine you're on. The pieces of the machine will transfer their velocity with the bowling pin, so to speak, of the ground and of the air. And it will give little pieces of the air and little pieces of the ground motion, velocity. And that velocity will keep getting transferred, and eventually it'll just look like heat. That's what it'll turn out looking like. But that's still momentum. Heat is momentum. Would be a really great thing they could say in here somewhere. But again, all of this that they're going to say could be said for momentum. So all of these rules fit perfectly for momentum. So they're in no way specific to kinetic energy, because every single one of these statements could be made about momentum. The chemical energy has been converted into kinetic energy, the energy of motion, but the process is not completely efficient and produces heat within the cyclist. Everything, all the energy sort of usually the transfers are from these complex objects that you've given, big objects you give motion to. It always kind of goes to heat and then back into an object and then back to heat and then back into an object. So it's always disguised as heat somewhere in its life cycle. I mean, you might argue that, all atoms, throughout their life cycle, they always go back to being hydrogen, and then they get built back into heavy elements, and they go back to being hydrogen. They go back to heavy elements, back to being hydrogen, that kind of thing. All right, the kinetic energy in the moving cyclist and the bicycle can be converted to other forms. So the other forms are really the same form. It's just giving momentum. So you're just giving your momentum, your velocity, fundamentally, to something else. For example, a cyclist could encounter a hill just high enough to coast up so that the bicycle comes to a complete halt at the top. The kinetic energy has now largely been converted into gravitational potential energy. I mean, clearly it didn't convert it into gravity. It lost it to gravity. Gravity took away all the energy. And, the good thing about gravity is that it will give it back to you if you ask for it. So if you go down the hill, you'll get back what you lost going up the hill. So that's pretty uncomplicated, but you really don't create anything called gravitational potential energy. The potential is in the location in space, and so by reaching that location, you reach a place where there's an avalanche and it's going to push you down the hill. Okay. That can be realized by freewheeling down the other side of the hill. Freewheeling. I mean, it's just kind of funny that they put freewheeling in, the sentence. It's just kind of, that's kind of, you could just say coasting. Since the bicycle lost some of its energy to friction, it never regains all the speed without additional pedaling. To say never is probably a stupid thing to say. You could just, again, make the argument that if you can reduce all contact that might absorb some of your energy, you will get back exactly what you put in. But in most cases, you can't avoid contact with the air and bugs and different things, and so those things will all take some of your momentum away. So you'll always, if you keep going up and down hills, eventually you're not going to have any more energy left. Since the bicycle lost some of its energy to friction, it never regains all of its speed without additional pedaling. So again, to say never is just a little bit going a little too far. The energy is not destroyed. It has only been converted. No, it's been transferred. So this word converted is a little dangerous, but you're not really converting it. You're just transferring it to different size bowling pins. The ground is covered in little tiny bowling pins. So you're just really hitting other objects, moving them. You're transferring your momentum. They interact with you. You give them your mass and velocity. I mean, you give them your velocity. You can't give them your mass. And now you have less total capacity to keep doing that. You're moving less relative to the world because you've lost some of your velocity by giving away some of your momentum. Another possibility would be for the cyclist to apply the brakes, in which case the kinetic energy would be dissipated through friction as heat and sound and vibration. And of course the brakes alone can't do the job. The rubber has to meet the road and be obviously the tire is going slower than the bicycle, and it has to essentially rub against the road. Okay, like any physical quantity that is a function of velocity, the kinetic energy of an object depends on the relationship between the object and the observer's frame of reference. So again, this whole try to make this into relativistic bullshit is just that. The truth is, I can move two objects, and I can say, oh, look, from my perspective, they're both moving the same amount. But the truth is, the planet could be moving in a direction, and actually, this one's not going quite as fast as this one. This one is actually going a little faster than this. This one's going much slower, and this one is going faster. It doesn't matter, though. There is an absolute space in which things move, and something always has to have the energy, okay? The thing that is, there is a thing that's actually got the energy. We just can't identify it because we're a biased observer, because we're moving as we're observing, so we're not seeing the event in absolute space. But they can't say any of that because they've declared absolute space non-existent, which is another, yes, it's just such a bad physics because they had no trial. Space wasn't afforded a fair trial. It was given absolute space was not given a fair trial. It was sent to a miserable dungeon without any good arguments having to be made, because of Einstein. Anyway, but they were already trying to do it, and that's the sad part of physics, because it was, it wanted to go wooey. It wanted to turn the physics into metaphysics, and they successfully, in many respects, did that. All right, so I don't know. Let's see. Like any physical quantity that is a function of velocity, that is like momentum. So instead of saying that, physical quantity, they could have said momentum. Like momentum, which is a function of velocity, the kinetic energy of an object depends on the relationship between the object and the observer frame of reference. Thus, the kinetic energy of an object is not invariant. But clearly it is. We just can't see it. There is an absolute fact about the event. The event can't happen unless some object is moving, right? Either this is crashing into this, or this is crashing into this. But something has to be doing the moving. Something has to be moving. Or both things are moving. They're just moving different speeds than what we're observing. But anyway. Okay, so that's probably enough. Spacecrafts use chemical energy to launch and gain considerable kinetic energy. So that's sort of a deception. I mean, they're using chemical energy, but they're really using momentum. They really are moving bits of matter, pieces of matter, and they're throwing them in the direction. And they're experiencing the equal and opposite. The spaceship is experiencing the equal and opposite reaction to the little explosion of energy. Every explosion of every bit of energy has pounds in both directions. So the core energy is something that's moving in both directions, essentially, is the argument. And so the chemical energy, you're saying, if I go positive, I have to go negative, and that's all you're doing. So you're throwing energy in one direction in the sense of momentum. You're pushing little bits of stuff and making it fly at a high velocity, which is a lot of momentum, and you're just getting the opposite of that. So calling it chemical conversion, yes, it's chemical energy. Yes, you're converting it, but the process of conversion has everything to do with momentum. There's no disconnect between the chemical energy and the word momentum. Momentum works very well to explain why the chemistry has momentum and how it manifests the momentum by expanding the size of atoms, by making a bunch of little tiny explosions, essentially. All right, to reach orbital velocity. In an entirely circular orbit, this kinetic energy remains constant because there is almost no friction in near Earth space. So again, the energy, if you don't have friction, you keep it. If you do have friction, that is, you interact with anything, you're likely to lose it. So that's all that statement is saying, is that there's always, the energy is always moving. And all you can do is lose it. I mean, you can't, that's it. So if there's nothing you interact with, you get to keep your energy. If you interact with something, you lose it. Now, there is energy you can lose, like in the form of photons, okay, in terms of you can radiate your heat. And you are, in fact, losing energy by radiating. But clearly, you're throwing away, in a sense, mass then. The force, it's in the form of energy, and the energy itself has momentum, the photons. So you are throwing away mass. All right, so I don't know if we need to do any more. It's probably enough for today and such. So I think it's just useful to go through some of this. I mean, the glaring history is that you can see it right on this page, this superficial description of the the kinetic energy controversy as it existed as a historical fact. They kind of just glibly washed over the whole thing, and they're basically admitting that the whole thing was based on one aberrant experiment. Dropping stuff into clay. The clay experiments didn't match all the other 99% of the experiments, and in spite of the fact that the 99 of the other experiments completely defended momentum, they said momentum is guilty, throw it in purgatory, and let's preserve the aberrant experimental experiment. Let's justify the silly proposition made by the Newton hater, okay, instead of recognizing that, yeah, Newton really was a good scientist, and his observations on motion were solid, and there was absolutely no good reason to feign some cause to change those descriptions, or even to reword. Newton was careful even how he worded things. I mean, yes, you could reword something a little bit better, but Newton did good work, and you're all just standing here right now pissing on Newton's head. And you might say, oh, that's not what I know, it's Newton derivative. No, it's not a Newton derivative. It's not Newton physics. It's not classical mechanics. You're just pissing on the good scientist and sitting there and, making a hero out of who really was not a very good person. He really might have just been overtly a thief, a con artist, and a social manipulator. And you really did pick the wrong black hat, white hat thing. You picked the wrong side. You're making a hero out of the villain, and you're double raping, the hero, Newton. All right, that's all that needs to be said, I think. So, this has been a DraftScience video presentation and such. Thank you for your attention.